All right, so now we're going to carry on with section one, which is the time value of money. We have actually an interesting derivation to go through, and then we're going to move on to chapter or section two, I should say, where we're going to be looking at the measurement of interest rate risk. Okay, so right here at the end of section one, we do have well, actually, first, before what we had just done last time was we introduced the two formulas for the future value of an annuity and the present value of an annuity. And I did mention that proving them is not too difficult, so we're going to give it a shot. So here's the future value of an annuity. And of course, the beauty of this formula is that you can calculate the future value of any number of cash flows as long as they're equally spaced and they're all equal to each other. Normally, an annuity takes place on a yearly basis, but sometimes you can see it also can happen over a monthly basis. For example, when you take out a car loan, you probably notice that the amount that you pay every month is exactly the same. So, same thing with the mortgage. So you could think of those as a special type of annuity where the cash flows occur every month instead of every year. And these formulas can be used for that purpose too. In fact, if you jump ahead a little bit, you can see that if you do have monthly payments, then that M in that formula just becomes 12. And that changes it from, of course, annual payments to monthly payments, and then you're all set. So it's a very powerful formula. But where did it come from? Okay, so we're going to end up needing to rely on infinite series to get to this result. So let's take a look at how this works. Okay, here we go. All right. So the present value of an annuity. Now, um, okay, we're starting present value. Hold on one second. All right. So again, we want to derive these just to see where they come from. So let's start with the present value of an annuity. So now, of course, the annuity has a finite number of payments. We'll call that N. Okay, and now C is a constant. It's the annual cash flow or the repeated cash flow. If it's monthly, like for mortgage, then C would be the monthly mortgage payment. R is the rate of interest. Now, the rate of interest is going to be consistent with the time frame. So if these are annual cash flows, R will be an annual rate of interest. If these are monthly payments, then R would be a monthly rate of interest. So we can see that there can be any number of periods, although it is finite. And what we can do is define X to be 1 over 1 plus R. One over 1 plus R. So if that's the case, then what we end up with here is PVA now suddenly equals XC plus X squared C plus dot 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 X to the N C. All right, well, there's nothing mysterious about that, but here's the interesting part. Oh, I see. I wrote them with the C first. It doesn't really matter, obviously. I'll tell you what, let's just change it to be consistent with the slides. Now, if we multiply PVA by X, we'll get CX squared plus CX cubed plus CX to the fourth plus. So now we're going to subtract one from the other. And if you look at it carefully, you'll see that all the terms will drop out except the first and the last. So there's these drop out, all the way out. So you end up with CX minus CX to the n plus 1. And then we can do some factoring. Actually, this is CX Okay, so now we can divide both sides by 1 minus x. All right, so what does that get us? Well, now we're going to make some more substitutions. And so this is where we are right now. But so what we're going to do is make some substitutions. In other words, we're going to bring back the definition of x into our equation here. And we're going to see what happens. So remember, we define x to be 1 over 1 plus r. So that means what we actually have here is this. So all the x's will be replaced with 1 over 1 plus r. Okay, so now what happens? Well, now we got to obviously simplify it. And so one thing we can do is multiply it across in the top term, top two terms. Oops. And let's see, where does that get us? All right, so now we have okay. Let me just neaten this up a little bit. All right, so you can see we're going to end up with a common factor here. Actually, I probably shouldn't have consolidated these two because let's do this. Now we can cancel some stuff out. We're going to have C. Okay, and that should take care of it. So let's go back and get the formula that we start out with. And you can see that except for writing this as 1 plus r to the minus n instead of 1 over to the positive n, it's the same formula. Okay, so in other words, that's it right there. That was our proof or derivation, I guess we should say, that this is in fact the correct value of the present value of an annuity. So that's why this formula looks like this. By the way, I do want to mention here at this point that there does exist in the financial markets an annuity with an infinite number of cash flows can be priced as. Wow, that's interesting. So this type of annuity is referred to as a perpetuity because you can see the word perpetual hiding there. And the reason for that is because what we're actually doing here is taking the limit of this case when n goes to infinity. This goes to zero, and we're left with C over R. Interesting. Now, you might not think this would be terribly useful because, of course, in the real world, when do you ever see a perpetuity? Well, you'd be surprised. There have actually been cases where bonds were issued in the form of a perpetuity. In other words, a bond, and we, by the way, we haven't started talking about bonds yet, so this might be a little premature, but a bond that provides interest payments forever, but no repayment of the borrowed principal is a type of perpetuity known as a consul. Now, again, you might say, well, there's no way anyone has ever actually done this. Well, the British government, whoops, consul with an L. Believe it or not, the British government issued consuls to finance the wars with Napoleon Bonaparte. I guess they're afraid that they might not be able to repay the principal before it became due. So they figured, well, it'll be safer this way. If we win, we'll just make the payments forever. If we don't win, well, what's the big deal? We won't have to pay them off anyway. So they were issued during that period. And there's been other periods in history where consuls have been issued. Now, eventually, the British government went out and found the owners of these consuls and they bought them all back. So they're not still out there paying interest, but they would have if they'd never been repurchased by the British government. So they have been issued occasionally throughout history, very, very occasionally. Once in a while, you see something that comes close, though. In the early 90s, Disney issued 100-year bonds known as Cinderella bonds. But that's an informal name in the market. No, Disney didn't call it that. I guess they figured somebody would buy them. So that's awfully close. That's as close as you're going to get to a console without it actually being a console. Now, another area where this will show up later on is that a preferred share of stock has features similar to a console or a perpetuity. Because what happens with a preferred share of stock is that you're basically getting more or less predictable stream of dividend payments, but you're not getting a whole lot of opportunity for capital gains. Okay, so a preferred share of stock provides a steady stream of income with very little growth potential. With common stocks, the ones that you normally think of as stocks, it's the other way around. You're not getting a whole lot from the dividends, but you are getting a lot of growth potential. So these are set up for investors who just need income. Okay, so a steady stream of income with very little growth potential. Another thing to keep in mind is that a share of stock has no finite lifetime. In other words, it doesn't have a specific maturity date. So let's call that a maturity date. So a company like Coca-Cola, which has been around more than 125 years, those cash flows will continue to go on forever. If you bought a share of stock when Coke first came around in the 1890s, it's still a valid share of Coca-Cola stock. So any dividends that were paid out over that period would have a lot of the same properties as a perpetuity, because no, it's not an infinite stream of dividends, but it's compared to our lifetimes, it certainly is. So, this idea of a perpetuity is not all that far-fetched in the real world. So, but think of it as the limiting case of an annuity. An annuity with an infinite number of periods becomes a perpetuity, and its pricing model is very simple. Um, so it ends up being C over R. Now we're going to do the same thing with FVA, future value of an annuity. We have a simple derivation here to show us why this is the case. Right, and so let's see, where does that come from? Now here, what we're going to do is rewrite it in a kind of an interesting way. So keep in mind, with the future value of an annuity, remember each cash flow is being invested uh, every year until year end comes along. So that's what we're assuming, by the way. With an annuity, there's an implicit assumption that all the cash flows are being reinvested in something else that's giving us the same rate of return. So um, here, we're rearranging it in terms of how many years the cash flows will be invested. So in other words, the cash flow received in year N is invested for 0 periods. So its future value is not just C, that you actually receive. This one, um, this is received in year N minus 1. Which means it'll be invested for 1 year. And that's why this has an exponent of 1. Also remember, by the way, I want to remind you that these two formulas we are working with now are ordinary annuities, which means that the payments start 1 period in the future, not right away. So that means this is the cash flow received in year 1. Now, year 0 was today. So this is received 1 year in the future. Therefore, it is invested for N minus 1 years. Okay, so that's the logic behind this equation. How many years is this cash flow being invested for, given that this is an N year annuity? So remember, the first cash flow starts in 1 year. So therefore, it is being invested for N minus 1 years. The last one is invested in year N. So it is invested for no years. So now we're going to make some substitutions, just like before. And so X will be this time just 1 plus R. Okay. And then, I see what's happened here. It's been rearranged. Okay, that's fine. And this one is just C, of course. So then it ends up with CX to the N minus 1 at the end. And then once again, let's try the same trick we had before. Subtract. Again, all the terms will drop out except the first and the last. So that equals that minus cx to the n. So we can do some factoring. Let's do that right now. Okay, and then we can factor out the c. And now we can replace everything with 1 plus r. All the x's become 1 plus r. Okay, so we have and that reduces to if you look carefully at that formula, let's oh, you know what, I just realized I'm wrong. This is negative. 1 minus 1 minus r, yeah. So that means we actually have now we're good. Okay, we're all set. Okay, I missed that negative. Okay. And that's how we derive the two formulas. Now, of course, in a case like this, if you were looking at trying to figure out the future value of a perpetuity, it would just be infinity. So there's no mystery about that one. All right. Now, bond pricing formulas. Now, I did mention before, we haven't really talked about bonds yet. So I just want to remind everyone, or at least introduce you to this concept of bonds. A bond is, as it says here, a debt security or debt instrument. And what happens with a bond, where the investor pays, well, let's just say the investor, um, the bond, let's think about this in English. Bond is a debt instrument that is issued with a price known as the face value. Okay, this is good. Or sometimes it's called the par value, which is usually, but not always, $1,000, at least in the United States. Every country's bond markets are a little bit different. So usually $1,000. The bond has a fixed maturity. And so during the lifetime of the bond, the issuer will make interest payments known as coupons for historical reasons to the investor every year until the maturity date. at which time the face value is repaid to the investor. Okay, so in other words, let's just make up a very quick, simple example. Um, Suppose that a bond is issued with a 5-year maturity, $1,000 face value, and what's called a coupon rate of 6%. The investor's cash flows will be okay. So in the initial today, year zero, we pay $1,000, and then next year we get $60. Why 60? Because that's 6% of 1,000. But in the last year, we get not only our $60 coupon, but we also get our face value back. So those are the cash flows that would be paid and received by the investor in this bond. Okay. And so this, and by the way, bonds, if you see how well organized these cash flows are, they're very predictable. There's a very strict structure to this. Bonds are an example of what are called fixed income securities because the amount of interest that you earn every year is fixed. It's decided in advance. It doesn't change. Okay, since the cash flows are fixed in advance. Now, just as a quick aside, bonds are issued by governments to cover their deficits, by corporations to invest, typically to pay for expenses, and also to reinvest in the corporation. So let's say Apple sits down and says it's time to design the next iPhone. We need $100 million in a hurry, or whatever it is. It's probably in the billions. Where do we get it from? Well, we don't have it laying around in the corporate vaults. So instead, we issue bonds to the investors. And so they give us money up front. We pay it back in stages. In other words, we give them interest every year until the final year, at which time we repay the money. And what we're hoping is that, let's say, the bonds cost us a 6% coupon payment every year, but the rate of return from building the new iPhone is 10% or something like that. Then, as far as we're concerned, it's a good deal because we're getting more back from our investment than it cost us to borrow in the first place. And also, bonds can be issued by domestic and foreign bond corporations and governments in the United States. It is possible to buy foreign bonds in the US, but they're all structured in a very similar way. So it turns out then that we can use the present values formulas we were just looking at to calculate the market price of a bond. Now, the market price of a bond can be very different from the face value of the bond. The market price is nothing but the present value of the bond's future cash flows. Which means that we can calculate it very easily as the present value of an annuity, the coupon payments, and the present value of a sum, the face value. We can calculate both present values, add them up, and we've got our results. So the interest rate that is used to compute these present values is known as the bond's yield to maturity. Often it's simply called the yield. The yield reflects several factors, including the maturity of the bond and the credit rating of the issuer, as well as the overall level of interest rates in the economy. So in other words, if you look in the Wall Street Journal, you see that Apple yield on an Apple bond is 6%. There's several reasons for that. Apple bonds are very safe. They have a very high credit rating. We don't know what the bond's maturity is until we look at the specific details. And right now, interest rates in the U.S. economy are relatively low levels, by historical standards at least. And so yield is a reflection of the return that investors expect to get when they own one of these bonds. Okay. So now a couple of details here I just want to mention. In the US at least, it is normal for interest payments to be paid on a semi-annual basis. So in the last example, investors would receive not $60 a year, a $30 twice every year. And that's where the name semi-annual comes from. That's just a convention. I don't know how that got started. The other thing that's of interest is the word coupon. Um, the word coupon, normally when you see the word coupon, you go to the supermarket and you buy groceries and they print out your receipt plus these little strips of paper that might say this entitles the owner to $1 off in their next purchase of paper towels or something like that. So, or in the past, you would have in the newspapers, you would have these coupons in these ads for supermarkets, and you have to take a pair of scissors and cut them out and bring them to the store to cash them in. So, how did this happen to be the name of the coupons, the cash flows in a bond? Well, until recently, ownership of a bond was demonstrated through the holding of bond certificates. Just like stocks, there were certificates, and if you bought a bond, let's say from AT&T, you would get this little certificate. Not little, it would probably be the size of a college diploma, and it would have all the details of the bond on it. And here's the part that is the most interesting. You may have seen, by the way, pictures of historical stock certificates. They're very nice. They're really works of art. They're intended to impress people with a corporation, and so that's why they look so amazing. But with the bonds, now keep in mind the period I'm referring to now is pre-computers. So I'm gonna see if I can find one that works for us. This I find from experience, this is very difficult. Oh, stock certificates are easy to find. There's so many of them because people care. There's something about bonds that makes people tend to think of them as kind of boring, not that exciting. Okay, now we're getting a little away from where. Um, let's be more specific here. Okay, I think we got a winner right here. Well, zoomed in on it, but whatever company this was, you can just barely make it out. I can see that in January of 1935, this little strip of paper on the top here is a coupon. And what would happen is somewhere on here it mentions a dollar amount, and you could take a pair of scissors and cut this off and bring it to the bank or mail it into the company, and they would send you a check for the size of your coupon. So if it says $10 on here, you would get a $10 check, and that would be your coupon payment because you're redeeming these cash flows literally with coupons on the bond certificate. That's part of the reason why it's so hard to find bond certificates with these coupons, because that means somebody never cashed in all the money they were entitled to. That's why they're called coupons. And they kept, even until way into the 70s, I want to say 80s even, you could still get bond certificates with the coupons on them. Eventually, computers made all that unnecessary, but that's where the word comes from. Anyway, so what's important here is this. On the day that a bond is issued, its market price equals its face value. On the day that a bond matures, the market price equals the face value. At any time between, as interest rates fluctuate, which they do, market price of the bond can rise or fall and will not necessarily the face value. Specifically, when interest rates go up, bond prices fall and vice versa. So there's always an inverse relationship between the level of interest rates in the economy and the prices of bonds. When rates go up, the present values of your cash flows go down, and so therefore so does the price of the bond. When rates go down, it's the other way around. Okay. So what we're going to see here in the slides is, oops, I know that's coming later. How do you actually price a bond? Oh, by the way, just as an aside, there's another type of bond out there. These bonds are known as coupon bearing for obvious reasons. There are also bonds in the market that do not pay any coupons. They're known as you can imagine, zero coupon bonds. So why in the world would you buy them? Because they are sold initially at a discount from the face value and then redeemed at maturity at the full face value. For example, a 1-year zero coupon bond with a face value of 1,000 might sell for, let's say, 925 when first issued. The investor pays 925 and then receives 1,000 at maturity. Instead of earning a coupon payment, the investor has just earned a capital gain of $75. But most bonds in the economy do actually provide coupon payments. Usually it's only the bonds with extremely short maturities that are sold this way. Okay, that's just the market convention. So that means that if you can see here, the price of a coupon bearing bond looks like this. So you can see that every year we get a coupon, except in the last year end, we get both a coupon and the face value. Now, this looks like a lot of work, but if you think of the coupons as an annuity, then what you can actually do is calculate the price of the bond can be determined by applying the present value of an annuity formula to the coupons and then using the present value of the sum or applying the present value of the sum um, formula to the face value. So you only need to do two calculations, and that will give you the market price of your bond. And the R in this case is what we meant earlier by the yield to maturity. And that's the part that can change every single day. All right, the C and the F are fixed in place. Um, Now, by the way, when you do buy a bond, the investor in a bond is actually entering into a contract with the issuer. This contract is known as an indenture. So the indenture contains all the details, such as the coupon rate, maturity, its value, and any special features the bond may contain. And there's quite a few that are fairly common features. It's all specified in the contract. Now, if the issuer fails to make any of the payments in a timely manner, then the corporation can be sued for bankruptcy. And that happens once in a while. It's not a common thing, but this is why it's important to know how creditworthy an issuer is. So in order for investors to know, to understand how much credit risk each bond has, there are ratings agencies, as they're called, such as Standard & Poor's, Moody's, you may have heard of these companies, Fitch, etc., that provide ratings for every bond in the economy. So you can consult those ratings to see how much risk is involved. Bonds with the weakest ratings must offer the highest coupon payments to entice investors to buy them. Okay, so that's how that works. In other words, if you, let's say, for example, by the way, I just want to mention quickly how these ratings work. Standard & Poor's ratings look like this. You've got, you're at the very top of the pyramid here, you've got AAA, AA plus, then AA minus, plus, A minus. Then it goes down to the B's, triple B plus, triple B minus. Now, this collection of ratings, these are all referred to collectively as investor or investment grade bonds. Then you have the so-called junk bonds, and they would have ratings like triple B minus. I'm sorry, I missed. There it is. That's why it's down there. Double B plus is the beginning of the junk bonds. B plus, B, oops, B minus, and then it goes down to triple C, and then we're getting to some really scary territory down here. Bonds in this neighborhood are right on the brink of bankruptcy, basically. And it goes down, I think it may go all the way down to D. Those are the really dreadful bonds. So anyway, the reason why I showed this to you is because I want you to see that if, for example, um, suppose that a AAA corporation issues bonds with a 4% coupon rate, a, let's say, double B plus corporation might have to offer investors, let's say, a 9% coupon rate in order to entice them to buy the bond. Otherwise, nobody will touch it with a 10-foot pole. I mean, there has to be a higher rate offered in order to compensate you for the risk of default, as it's called. When the issuer fails to make the payments on time, it's known as default. Default is bad news. When there's a default and there's a bankruptcy, the assets of the corporation are liquidated and sold and distributed to the bondholders. But you might find yourself getting back half the money you invested in a bond when this happens. It's not a good situation. So anyway, going back to the formulas, this is the simpler version. Well, in a way it is, but we just consolidated all the terms on the left into this one. But you can see more clearly maybe that what you have here is the present value of an annuity. And the present value of the sum. And so you really realistically only need the two terms to come up with the price of a bond. All right, so here's a treasury bond. Now, this bond is issued by the U.S. Treasury Department. Now, the U.S. Treasury is responsible for raising funds for the U.S. government. And because they always have a deficit, always it's a huge deficit, the Treasury issues bonds to the public. To raise funds to cover the government's deficits, which is, every year. Now, these are collectively known as Treasury securities. Now, they're actually, in fact, let's take a look. There's a website where you can look up the yields that are being offered to these treasuries. I don't think this. Oh, this is the main page. Data. This is where we should go. And so, what's going to happen here? Let me save this link. And so you're going to see across the top here, these are the maturities, and down here you can see the dates on which these applied, and then you've got the actual yields. So this goes all the way back to the start of the year. So um, that hasn't changed much this year. This set of numbers is often referred to as the term structure. It's referred to as the term structure of interest rates. And a graph shows this relationship is known as the yield curve. So what you're seeing up here is that the Treasury offers maturities ranging everywhere from 1 month to 30 years. That's unusual. Corporations typically only offer very long-term maturity bonds, like 10, 20, 30 years. The Treasury Department has everything. So everything under the sun from 1 month to 30 years. So there's actually separate names for these different securities. So in the Treasury market, bonds with maturities from 1 month to 1 year are known as treasury bills. So even though they're technically bonds, they're very short-term bonds. Bonds with maturities from 2 years to 10 years are known as treasury notes, and the bonds with maturities from 20 to 30 years are known as treasury bonds, actually. They're actually called treasury bonds. So we've got treasury bills, treasury notes, and treasury bonds. Although technically they're all bonds, this is the market convention. Now, what's interesting here is that treasury bills are sold as zero coupon bonds, meaning they're sold at a discount from the face value. The rest are sold as coupon bearing bonds. Okay, and there's other differences too, but those are the important ones. And by the way, yield, I'm going to see a lot of this as we go along. Yields on treasury securities are considered to be the risk-free rate of interest for a given maturity. And that simply means risk-free, in this case, means free of default risk. Okay, now why is that? Well, the government's in a unique position. A corporation can run out of money, end of story. They can go out of business. The government can't go out of business. If they run out of money, they have other options. They can raise taxes, for example. They can sell off assets that they own. They have other ways of raising money. So they're not going to allow themselves to not pay these treasury notes, treasury bills rather, and treasury notes and treasury securities, because that would ruin their credit rating and would cause the cost of borrowing to go up a lot. So they'll do whatever it takes to make sure you get your money. So this is the one type of security where we don't have to worry about default risk. For the rest of them, there's always a chance something could go wrong. And that's why those ratings exist, so we can tell them apart. Well, yes, as we go further into the course, we'll see, especially when we're looking at derivative securities, that risk-free rate of interest will be a hugely important concept. All right, now, I think what's coming up next is an example. Oh yeah, here it is. So we have the face value of 1,000, the annual coupon. Just to keep it simple, we're going to use an annual coupon of 70. The 4-year rate of interest, which is the yield to maturity, by the way, is 5%. So this is what the market price looks like. So 4 years. Now, by the way, this, even though this is a 4-year bond, that doesn't mean necessarily that it was issued right now with 4 years to go to maturity. It could have been issued, let's say, it could have been a 30-year bond issued 26 years ago. It could have been a 20-year bond issued 16 years ago. Right now, at this point, all we know is that there's only 4 years left. So you notice how this coupons are $70. The yield is 5%. So when you actually calculate those numbers, those present values, they add up to $1,070.92. That is the market price of this bond. And you can see it's higher than the face value. Now, here's another interesting twist. When bonds are first issued, their coupon rates are chosen to match current yield to maturity of a bond. So, in other words, for example, if a corporation issues a 30-year bond and the corporation, the credit rating of the corporation is such that its bonds have a yield to maturity of 7%, the corporation will choose a coupon rate of 7%. Okay. So in other words, this is the convention. Your yield will determine your coupon rate when it's first issued. The coupon rate never changes, but the yield to maturity does. This is why the market price of a bond fluctuates over time. All right. So, and of course, we could just go ahead and use our wonderful annuity formulas, and you'll get the same thing. Now, this is where it gets interesting. By the way, if you were to take, we didn't get to this point yet, but suppose you took a bond and recalculated its price with different yields to maturity. Let me see. I don't think I have an example of this right now, but if you were to take this bond and you wanted to know, well, what would be the price if the yield was 6 or 8% or 3% or whatever, and you did it many, many times and you plotted the relationship between the two, you'd end up with this special graph, which is known as the price yield curve. Now, what's interesting about this is that clearly the relationship is inverse or negative, which means the slope of this curve has to be negative, but it's not a straight line. It looks something like this. Oh, now that is interesting. So clearly the first derivative of this function is negative. So if you can think of the price of the bond as P of R, then the first derivative is clearly negative. You have all these slopes of the tangent lines along this curve are negative. But if you notice, as you go to the right, as x increases, the slopes are becoming less negative. So that means that the second derivative is positive. And that means that the curve is not only not linear, it's said to be convex to the origin. Convex. Okay. Now we'll see when we start looking at the risk measures how important this proves to be. Now you might think, well, oh, what's the big deal? This is actually very helpful to the bond investor. All right, here's why. Because let's just imagine that you have a bond and let's just say that at the moment, the yield is 7% and the price is 1,000. If the yield goes up to 8%, say the price drops to 920. But if the yield drops to 6%, the price goes up to 1092. Now, of course, I just made up these numbers, but I mean, the principle is the same. So what this is showing us is that there's an asymmetry between the gains and the losses to the investor as the yield to maturity changes. So if the yield rises by 1% from 7% to 8%, the price drops by $80. But if the yield falls by 1% from 7 to 6, the price rises by $92. So in other words, you see how that's helping us. We gain more on the upside and we lose less on the downside. If we had a straight line, it would be the same on both sides. So the convexity is actually helpful to the investor. Okay, and we'll revisit this discussion when we get to section 2, I should say. So this is our price yield curve. Also, I want to point out that some bonds have more convexity than others, and we'll discuss that as well in the next section. Some of them are very highly convex and some are not very convex at all, but this relationship is very close to being linear. All right. So that price yield curve is going to prove to be a huge deal in this area. Now, one thing I do want to point out here, which is kind of interesting. Based on the way it's drawn, the price yield curve, we'll call it P of R, the price yield relationship is monotonically decreasing. Ooh, all right. Remember what that means. It means that when R is rising, P is always falling with no exceptions and vice versa. This guarantees the existence of an inverse of P of R. So as a result, we can do one of two things here. Find the price of a bond from its yield, or we can also find the yield of a bond from its price. Oh, no apostrophe. And so we're going to do exactly that. There's just one problem, though. We don't have a lot of information about every bond. In other words, you don't have an infinite amount of information about each bond. They're all somewhat unique. And so what that means is that it's not realistically possible to actually estimate a functional form for P of R. It has to be sort of estimated from sporadic, let's say, market data. So we can't take the inverse of P of R to solve for yields. Instead, we must estimate it. We must estimate yields using numerical methods, specifically root finding techniques. Oh my God. So it sounds like we're getting into some extremely deep water here. And the ones that we're going to consider are the method of bisection, Newton-Raphson, and the secant method. So you may have heard of these before. This is getting into a more specialized area of math called numerical methods. You find this either in a computer science department or a math department, or possibly both. And so these techniques are reserved for cases where we don't have necessarily the ability to estimate a function properly. Instead, we have to estimate it. Like you might remember from calculus, the trapezoidal method that's used to calculate the area under a curve. And then you take the limit and that gives you the integral that you need. So, but even then, we're assuming that we know the function itself. Here, we don't have that luxury. So we're going to try these, or at least understand how these techniques work to see how they look for a solution. Of course, they all have their own advantages. They all have their own disadvantages. But for example, the method of bisection takes the longest, but it's guaranteed to converge to the correct solution, whereas the other two, they can get stuck, so to speak. So anyway, I think we may as well save this for the next discussion because it is fairly involved. And but I think you'll find it very interesting. And when this is done, we're going to move on to our discussion about risk, interest rate risk. We're going to define a new measure which helps us directly compare the interest rate risk of different bonds to each other on a side-by-side basis so we can make decisions about which ones to buy and which ones to avoid. Okay, so in other words, if you're a bondholder, aside from credit risk, the biggest fear that you have is that interest rates will fluctuate and that will reduce the value of your bond. So we have to consider not just credit risk, but also what's called interest rate risk. All right, anyway, I guess we can stop here and it's kind of like a cliffhanger. You want to know what's coming next, but don't you worry. It'll be very soon before we're ready for another session. So I'll see you then. Okay, so now we're going to wrap up section one. We've got some important details here to look at. And so what's happening here is that up to this point, we've been using the yields on a bond to calculate its price. But it turns out that often it's more useful to be able to take the price of a bond and use that to calculate the bond's yield. Because prices are directly observable in the marketplace, whereas the yields are actually implied by the terms and conditions of the bond. And so if you remember the price yield curve that we defined once before, we have price in the vertical axis, yield on the horizontal axis. The curve looks something like this. It has a downward slope, of course, because the price and the yield go in opposite directions, but it's also not a linear function. It is a convex function. And that basically means that in this case, at least, the first derivative is negative. The second derivative is positive because the slope is becoming less negative as we increase the yield. Also, there is a geometric way of doing this. We can prove that a curve is convex if we do the following. If we draw a secant line to the curve, and everywhere that secant line is above the curve, that's another way of proving that this function is convex. Okay, so by constructing a secant line through the price yield curve, we can see that the secant line is everywhere above the price yield curve. which indicates that the curve is convex. Okay, now that actually proves to be advantageous for the investors, as we're going to see in the next section, because there's an asymmetry between gains and losses. So if, for example, let's just say that this is our price yield curve, and initially with a yield of 5% and a price of 1,000, the yield goes up to 6%. Let's say the price drops to 950. And when the yield drops to 4%, the price goes up to, let's say, 1070. The important detail here is that in one case, we moved up by 1%. In the second case, we moved down by 1%, but the impact on the price is different. Okay, so in other words, you can see that when the yield rises by 1%, the price of the bond falls by $50. When the yield falls by 1%, the price of the bond rises by $70. So that asymmetry between the two is because of the convexity of the curve. Okay, so the convexity of this function is responsible for the difference between the two cases. In other words, if the relationship was linear, then we would gain or lose the same amount. Okay, but instead, as you can see, investors are happy because a drop of 1% in yields adds $70 to our bond price, whereas an increase in yields by the same amount only reduces the price by $50. Okay, so convexity is a very valuable property of a bond. And again, we'll see in the next section that convexity is a measure that we can define to help us understand how curved this function is for different bonds in the economy. One more thing I want to mention before we go any further is that percentages can be somewhat ambiguous. So there's another measure of changes in interest rates that we often run into in the financial markets, and that is this notion of basis points, or sometimes abbreviated BP or BPS. And so the way it works is this: 1%, which is 0.01, is defined as 100 basis points. 0.1%, 0.001, is 10 basis points, and 0.01% is 0.0001, which is 1 basis point. So why do we need a measure like this? Well, like here's an example. Let's say, suppose that yield of a bond is currently, like we saw here, it's currently 5%. If we say that the yield has increased by 1%, this could potentially mean one of two different things. The yield increased from 5 to 6, meaning by 1%, or the yield increased from 5% to 5% of 5, I'm sorry, 1% of 5% to 5.05%. Okay, so in other words, because this is English, it can be very ambiguous. If we say the yield increased by 1%, then it could, in principle, mean either that it went from 5 to 6 or from 5 to 5.05. So you can see we have to be careful about that. So with the basis point system here, it's very straightforward, because this, in the first case, we would say that the yield has increased by 100 basis points. And in the second case, we say that the yield has increased by 5 basis points. And so it's pretty clear what we mean in this case. In other words, you often hear the term basis points. And in fact, one of the measures of risk that we'll see in section 2 is actually based on the notion of basis points. So we want to be aware of this. All right. Anyway, now with all that being said, here's what we're building up to. Um, you can see that the price yield curve is monotonic. Specifically, it's monotonically decreasing. So you can think of this as P of X or P of Y, actually. The price of the bond as a function of its yield is monotonically decreasing. And that means that Y1 less than Y2 implies that PY1 is less than PY2 for all Y. No exceptions. Okay. So why does this matter? Because this implies or guarantees, and it doesn't have to be monotonically decreasing. Either way, as long as it's monotonic, the function is guaranteed to have an inverse. Why does that matter? Because in the case like this, as you can see, the price of the bond depends on the yield. But you could also make the case that the yield depends on the price. I guess you could write it as Y of P. Um, Actually, you'd probably be better off writing it like this. Okay, so the yield of a bond is not directly observable in the market. It is implied by bond's price, maturity, coupon payments, etc. In other words, all the features of a bond combine to tell us the yield of that bond, but it is implied by the other variables. The market price of the bond is directly observable in the marketplace and is a result of supply and demand. So therefore, it is usually more useful, is often, let's say, useful to be able to compute um, the yield of a bond from its price. Okay. Now, unfortunately, unlike the price, taking the price from yield is easy. It's just a question of calculating present values. Okay. The price of a bond can be easily calculated as the present value of the bond's future cash flows, where the discount rate, the rate at which we're discounting the cash flows, is the bond's yield to maturity. Right. So remember the way we did this in the slides. Let's go back a bit. Here it is. Oh, actually, I realize now that these are R's. All right. Every half the books in the market use R, half of them use Y. I'll tell you what, just to avoid confusion, let's go back and change all these Y's to R's, just so that it's crystal clear that we're talking about the same thing. Okay, very good. Okay, so now we got that straight. Okay, so here's the price. So it's easy to calculate the price, and remember too, the R is the yield to maturity. And so finally, the yield to maturity is defined as the unique rate of interest at which the present value of a bond's cash flows equals the bond's market price. Okay. So in other words, if we tried anything else, if R is too high, that means the bond's price will be too low, and vice versa. Okay. Now, so here's the issue we're up against. In order to determine the bond's yield, it is not usually possible to invert this function and solve directly for R. That would be wonderful, but it doesn't work that way. So instead, we have to resort to numerical methods. Specifically, root finding techniques, they're called. Okay, so remember now numerical methods are simply a way of finding the value of a function without actually having knowing the function itself. So in other words, we have to use approximations sometimes. And so there's a whole branch of mathematics called numerical methods, and that's all that they do. It's kind of an interesting area of study, but every situation is a little bit different. So here, it turns out there are several of these available to us, and we're going to consider all three of these and just understand what they're doing. And they're referred to as the method of bisection, the Newton-Raphson method, and the secant method. These are all available to us to solve for a case like this, where we're trying to invert a function without actually inverting it. In other words, to use numerical methods to find the inverse of this function, or in our example, to solve for R. So the method of bisection is the most straightforward one. And so what it essentially amounts to is this. Um, the way I remember the first time I ran across this in one of my books, the way they described it was like trying to find a lion in a desert. I mean, there's a strange analogy, but what they're basically saying is that imagine here's your desert and here's your lion. All right, well, it looks like a rat, but let's say that's your lion. So what you do is you cut the desert in half and you say, well, he's not here. So let's cut this remaining half in half. Well, he's not here. Let's cut this in half. And let's cut this in half. And eventually you have to find the lion. If you keep cutting the area in half, eventually you have to find the lion. And so it's a brute force approach, meaning that you're going to use a lot of steps, but you will eventually find what you're looking for. It's not as efficient maybe as some of the other methods, but it does definitely work. Some of the others, there's no guarantee that they will find the solution. This one is, you will definitely find the solution. Okay, so, and of course, you notice the name that bisection refers to the fact that you're taking whatever area you're looking at and cutting it in half every time. So, here's what we have to visualize. Now, by the way, I do want to mention here that when you're doing this with yields to maturity, what we have to do is make sure that the yield curve itself has some regions that are positive and some that are negative. Otherwise, this technique won't work. Okay. So in other words, if you notice, what you've effectively done is taken the actual price yield curve and shifted it down by the price of the bond. Or in other words, think of it as subtracting that constant from every point along this curve so that you end up with this. And right here is what we're looking for. Okay, what you're seeing right there instead of a zero here, we have the market price, and this is the bonds yield to maturity. So in other words, in order to use the technique we're about to use, you can't just apply it directly to the original price yield curve. We have to have an area where it's positive, where it's negative. So this is how it's done. All right, so now how do we find this point? Well, we're going to choose 2 points on either side. So by the way, we're going to use slightly different notation here. We're going to call this f of x. And so you can see what's happening here is that here's where it crosses. We need to find 2 points that are on the outside of this intersection with the horizontal axis, meaning that A has to be less than this point and B has to be greater than this point. Otherwise, we can't find what we're looking for. So in other words, you would never put B over here or A over here. One has to be where the curve is positive and the other has to be where the curve is negative. Now, once we've determined that that's indeed the case, what matters is now the signs of f of A and f of B. So in other words, if f of A times f of B is negative, that means that A and B are on either side of the root, it's called. Right here, that's the root. That's what we're looking for. And or sometimes we say that A and B bracket the root. All right, without that, none of this will work. All right, so we have to make sure that part is in place first. Now, what comes next? We're going to establish a midpoint between A and B. All right, so let me copy this in here so we can see it better. So once we've established that these A and B bracket the root, we need a midpoint. Here's the root. Let's say this is C. C is the halfway point between A and B. So when I put the C there, one of 2 things can happen. Either A and C are on the 2 opposite sides of the root, or B and C are on either side of the root. We have to figure out which is which before we can proceed any further. So you can see here that f of A is positive, f of C is negative. Which means that f of A times f of C is negative. And that means that A and C bracket the root. But as far as B is concerned, we don't care about B anymore. In other words, what we're going to do now is once we've established that this is the case, we're going to redefine B as this point. Okay, so see, this is how we're cutting the area in half. Like it's kind of like with the lion in the desert, but it's a little bit different because suddenly that C that we just defined is now the right endpoint of the interval that we're studying. And now we need another midpoint. Okay, let's say that that's here. So now with the new f of C has the same sign. It has the opposite sign of f of B. Okay. So the new f of c, positive, f of b is negative. Their product is negative. So now all of a sudden, this c becomes the new a. And then we need another midpoint and another and another and another. And so you can see what's going to happen. We're going to keep alternating back and forth between the two. We're going to try different midpoints, test the signs, and see whether we now have a new left endpoint or a new right endpoint. Eventually, we're going to find the lion. In other words, the brackets will get awfully close. And now, of course, it'll never perfectly line up here. I mean, there will always be some inaccuracy. So before the process starts, we must establish a level of tolerance, it's called, which simply means how close do we need to be to the true root, or yield in this case, um, to be acceptable. Because otherwise, this will go on forever, literally forever. Okay. So if you decided that you need to know the yield within 0.0001, well, that's fine. It'll stop when you've gotten closer than that. Okay. So you can establish now, of course, lower the tolerance that is needed, the longer this process will take. But it still won't take all that long. I mean, we're using modern computers that can execute a large number of commands in a very short period of time. So, when these methods were first invented, there weren't any computers. It was all done by hand. So efficiency was critically important. And it still is, but it's not nearly as important as it was, let's say, in the 1950s. So even if this method of bisection isn't the most efficient method in the world, the fact that it's guaranteed to converge to the correct solution is a very powerful recommendation for it, because it's not going to be that much more time consuming than the other two, where there can be problems finding the right solution. In fact, they can get into a loop where they never do find the solution. So this is a very popular method, even though it might seem inefficient compared to the other two, because they have a different way of reestablishing the upper and lower limits. And for them, if the function is well behaved, we can often find the root that we need in just a handful of calculations. Okay, this might take a while, but again, at least we know that we're guaranteed to find the right answer. So that's the logic behind this method. Now, Newton-Raphson, by the way, that is Newton, our old friend Newton who invented calculus and half of physics, I guess. Newton-Raphson is very powerful, but it does require us to calculate the first derivative of our function many times. Now, that could be a real problem here, because one of the unfortunate things about the price yield curve is that the price yield curve is not an observable function, because there are only a handful of bonds available to construct the price yield curve. In other words, that price yield curve covers every possible yield from 0 up to whatever. We don't have enough information in the market to construct the entire curve. What has to happen here, there's a special technique going on behind the scenes. The curve is completed with one of several techniques. One of the more popular ones, which we're not going to have time to get into here, but it's something called cubic splines. So in other words, if you have to visualize, imagine that this price yield curve treasury market looks like this. Now, here's the problem. Even the treasury market only has a handful of maturities to choose from. So what's going to happen is if we try to construct this curve, you might have, let's say, well, all right, well, you're going to end up with gaps. This is what I'm building up to. It's not a continuous function. This function is not observable. And what has to happen is everywhere there's a gap, we have to find a way to fill it in. So the cubic splines are basically a special type of polynomials that are well suited for this type of application. In fact, you could think of them as being somewhat like a Taylor series, where you're sort of approximating a function with a polynomial of some kind. Okay. So that's kind of more like what you're actually getting. And so in other words, why did I even bring this up? This means that finding the first derivative of this function is not realistic. I mean, you can do some approximations, but you're not likely to be able to find the actual first derivative because we don't actually know the full function. And even if we did, it's assumed to be smooth and continuous, but that may not actually be the case in practice. So that what that means then is that Newton's method is going to be a problem for something like this. But if you do use it, this is what it looks like. In other words, for each x, xk we're going to call it, to get to the next x, to get closer to the root, we're going to take the current xk, as it's called, and subtract the ratio of the function evaluated at that point over the first derivative evaluated at that point. So now this is hard to draw, but let me see what I can do. Imagine we start, and this one requires a starting point of some kind. Let's say we start here. The next point might be here. And then we might have this point. And then we might, eventually we'll get to what we're looking for, but it's possible that we'll just need a handful of slopes to get to the root that we're looking for. But it's also possible that if the function is not particularly well behaved, you can get into a case where the slopes are just, say you're trying to do a sine wave or something ridiculous like that. You might find that the lines that you're generating, the tangent lines that is, are just alternating back and forth, and they will never converge to the correct value. So that is the kind of problem you could potentially run into with Newton-Raphson. For other types of functions, it works great, but for this situation, it's maybe not the best choice. Anyway, and then we also have the secant method, which doesn't need a derivative, but it does require a lot of information. You can see that this one could really take a lot of computational power, although if you're lucky, it might converge quicker than the method of bisection. And of course, remember the difference between a tangent and a secant. The secant cuts to the curve twice. The tangent just touches it at one point. Okay, so that's why we need so much information to come up with the secant method, because you need both of those points where the line is cutting through the function. And so this one can be very time consuming. And again, you run into that problem where the way it's designed, it may not necessarily converge to the right answer. So, if you really need to calculate a bond's yield to maturity, you might be better off using the method of bisection in spite of the fact that it could be somewhat slow. Okay, so now there's other methods too, of course, but the idea here is that once again, the yield of a bond is implied by the bond's price and other terms and conditions, or other features, let's call it. Whereas the market price of the bond is directly observable in the marketplace. All right, now, with all that being said, we can move on to section 2, where we're going to introduce some measures of interest rate risk. So now, why is this so important? Um, Given that bonds are priced as the present value of the bond's future cash flows, and we have a copy of that formula right here, or I thought we did. Here it is. So if you look at this algebraically, you can see very clearly that if you differentiated this function with respect to R, it's going to be zero. Sorry, not zero, negative. It's going to be less than zero. Okay. So in fact, this is why the slope of the price yield curve is negative. So it's guaranteed to be negative. And so therefore, yields and prices move in opposite directions. Okay, so that being the case, even bonds with no credit risk, like treasury securities, expose investors to what we call interest rate risk. And all that means is that if you own a bond investors can lose money if interest rates rise. Okay, now what's interesting here is that each bond's sensitivity to interest rate changes is different. For example, if market rates rise by 1% or 100 basis points, one bond may lose 0.5% of its value, and another bond might lose, say, 4% of its value. Okay, so each bond has a different sensitivity to changes in interest rates. And so therefore, it's important to have a measure that we can use to compare them with each other directly. So it is important to have a measure that can be applied to any bond, which makes it possible to compare their sensitivities to interest rate changes directly. So you take a bunch of bonds and rank them from the least sensitive to the most sensitive. Okay, that's an important detail. So what measures can we use to measure the bond sensitivity? Well, there are quite a few to choose from, but we're going to start with a couple of very important cases for historical reasons. And they're known as duration and convexity. There's that word convexity again. Convex comes from the curvature of the price yield curve. Okay, so two of the most widely used measures of interest rate risk are known as, and then we have duration, as you saw, and convexity. Now, there's a long, oh, what happened here? Uh-oh. All right, let me move this stuff that I just created. Yeah, somehow it got put in the wrong spot. Let me just make sure everything's set up correctly. I don't want you to have confusing notes, that's for sure. All right, it looks good now. All right, I think we're going. All right, I don't know how that happened, but there we are. All right, now there are multiple types of duration measures. It's not, there's not just a single one. The first type is known as a Macaulay duration after the inventor or the developer, I guess might make more sense, the developer, whose name was Frederick Macaulay. A more modern version of this is known as modified duration. It has more useful properties for analyzing interest rate risk than Macaulay duration, which which by the way, Macaulay was an actuary. And what was he interested in studying? And I don't remember, he worked, it may have been an insurance company that he worked for, who wanted to ensure that a financial institution um, always had enough funds on hand to cover its potential liabilities. As an example, an insurance company collects premiums and then pays out claims as needed. So how do they make sure they have enough money? Well, the premiums are invested typically in something very safe, such as treasury bonds. And hopefully the returns to these investments will ensure that no matter how many claims take place, the insurance company will have enough money to cover them. So in other words, what you're trying to do is say, in this example, the invested premiums or the treasury securities that we're invested in are assets, and the potential claims against the company are liabilities, meaning that we potentially could have to pay out money. So the goal is to ensure that the interest rate sensitivity of the assets and liabilities is as close as possible. All right. So if instead, um, let's say the sensitivity of the assets is greater than the liabilities, an increase in interest rates will reduce the present value of the assets rate more than the present value of the liabilities. Those they'll both go down, but the value of what you have to pay for your claims with has fallen more than the claims themselves. So you can see we don't want this. This is not what we want to. Insurance companies are conservative because they don't want to run out of money, and of course they're heavily regulated too. So Macaulay's idea was to make sure that we have a way of determining if there's an imbalance in the sensitivities of our assets and liabilities, because if there is, we have to do something about it. Because before he came along, there was really no way of saying, listen, these assets are more likely to be affected by interest rates than these liabilities. There is no way of directly measuring them. So his measure turned out to be hugely important. And of course, this is why it was named after him. But as far as investments go, this measure, Macaulay duration, is difficult to interpret. Let's put it that way. It's not really the best choice for analyzing an investor's bond holdings. For this, a better measure, and one that's closely related, by the way, is known as modified duration. I don't think anyone knows who invented it because otherwise their name would be attached to it. But modified duration has the advantage that it can be interpreted as a derivative. In other words, well, we'll see when we get to the definition. A calculus derivative, I mean, not a financial derivative, a calculus derivative. And so that makes it much easier to measure the risks of these different bonds in our portfolio, compare them directly with each other. We're not interested in the assets and liabilities of a corporation. We're looking at individual bonds and how much their value might fall if interest rates go up. But luckily for us, the modified duration is so straightforward. It's almost amazing how it's just this close to the Macaulay duration. Once you know the Macaulay duration, it's not hard to convert it into modified duration. The convexity is a second order condition in the same way that the second derivative is the derivative of the first derivative. The convexity is a second order condition and can be thought of as the sensitivity of duration to changes in interest rates. In other words, the duration itself is affected by changes in interest rates. It's not a constant. So it's often important to be able to incorporate both duration and convexity in our measures. So, and a lot of this is going to sound very abstract until we actually do some examples. So, and when we do start using examples, we're going to have to do these in Excel because otherwise it'll take forever. But yeah, you can see the Macaulay duration. It's kind of an interesting idea. It involves the time. It incorporates not just the present values of these cash flows, but the time at which they're received. And we're going to go through a lot of numerical examples here, and then we're going to try to make some sense out of them, and we're going to see how they relate to modified duration and how it can be calculated. So you can see we got a lot of work to do here. So, oh, and here's how, again, how we show that a function is convex. This is the geometric argument, and we'll take a look at that. But anyway, so we'll be getting back to this next time we meet. So hopefully you've enjoyed this introduction to interest rate risk. But yes, we do have a long ways to go here. So we'll pick that up next time.